Okay. Hello everyone. Today we will gonna do electrophilic aromatic substitution reaction. First of all, what is this electrophilic aromatic substitution reactions? These are basically the reaction of the aromatic system. For the reactions of the aromatic compound in which the electrophile replaces one of the hydrogen in the aromatic compound is called the electrophilic aromatic substitution reaction. Now the general electrophilic aromatic substitution reaction. This is basic, and this is exactly like the alkenic system. As in the alkenic system, the pi electron attack on the electrophile. As we can have the example over here. This pi electrons attacks on the electrophile. That is basically partial positive and this is partial negative. Okay, and this will then leave. Here the electrophile will attach, and here it will form the carbocation. This carbocation is then attacked by the nucleophile. That might be this one. This is an attack over here, and it will then result in the formation of the addition product. As we see that aromatic system also have the pi electron. This is the most simplest aromatic ring. It has the 6th pi electron. It means that it is electron rich species. First of all, in the aromatic substitution reaction, that electrophilic substitution reaction, these pi electron attack on the electrophile. So before do this reaction, the general mechanism, we must have to understand that aromatic electrophilic substitution reaction only occur with the strong electrophile. Strong electrophile is needed for the aromatic electrophilic substitution reaction to take place. Okay, basically the electrophilic aromatic substitution reaction take place in the 2 steps. First is the formation of cation, as is exactly happened in the alkenic system. This is the uranium ion. This ion is basically stable because of the resonance. And the second step is the removal of the proton. This removal of proton is basically because that aromatic system, for the aromatic system, this is not very easy or not possible to lose its aromaticity. For the aromatic system, as the aromatic system is very much stable, so it will tends to form the aromatic system again. So the proton will remove, and it will then regain the aromaticity of the system. As we will then see through the example, this is the general example. As we said, this is the pi electron rich system. So this is the partial positive, this is the partial negative. This is the electrophile, and it will not behave as a nucleophile because it is the electron-rich species. These electrons, pi electrons, will attack on the partial positive charge, and these will then leave. It will result in the formation of this at once this carbon, the electrophile will attach, but on the other carbon there is its valence is not filled, so a positive charge will come over here along with a negative. Now it also has a proton over here, and it also has a proton over here, and now this is act as a nucleophile. It will then attack on the proton, and that is attached to the carbon atom having the electrophile. Both of the electron of this bond will become the part of this ring, and it will then regain its aromaticity. Now at this stage its aromaticity is lost. Aromaticity is lost. Now this will attack over here. These electrons come again, and in this second step the aromaticity will regain, and we are provided with the substituted product. Now we will see a little bit of its explanation. That now the basic question is this: is this species is a transition state or the intermediate? This answer will come that when this when the positive charge come on this ring like this aromatic system undergo different resonance structure, but which can be explained by the Kekulé structures. So hence here is proved that this species and this uranium ion is not a transition state. It's basically the intermediate. Now we can see that this here the aromaticity is lost. This is the non-aromatic compound, but it is stable because of the resonance. Now we can say that here we have the 6 pi electron, but here we have the 4 pi electron, and we have only this carbon atom sp3 hybridized, and the remaining 5 carbon atom, the sp2 hybridized. 5 carbon atoms are sp2 hybridized, and 1 carbon atom is sp3 hybridized. Now we have the 4 pi electron. The 4 pi electron then resonates over the 3 over the 5 sp2 hybridized carbon atom or the p orbitals, and it will then stabilize the intermediate form. Now as in the first step, as you see here, the benzene ring attack on the electrophile, this step is the highly endothermic step. Why it is endothermic step? Because the aromaticity of the system is lost. That is the most important factor of the stability of the compound. When the aromaticity is lost, we have to provide a lot of the energy to take place this reaction. Okay, and the second step, as the first step is the And we said that first step is a slow step. So it is rate determining step. Rate determining step, and while the second step is a fast step. Second step is a fast step, and this is the highly exothermic step. Why this is a fast step? Because the molecule, because the system. Here we see that that was the non-aromatic. That is the aromatic, because the aromaticity of the system is regained. So this step is very much fast, and it is the highly exothermic. This step will not take part in the redetermining of the system. Now we can see the energy diagram. Energy profile will say that first of all, this system is of the lower energy. When this approaches the electrophile, its energy will increase to the higher state of all of these processes, because as a result of this process, the system will undergo the loss of its aromaticity. Now, the second step is the formation of the uranium ion. After the uranium ion, when the nucleophile A negative will approach, and it will abstract the proton from the system, it will also of the high energy system, and after that, when it will remove, and both of its electrons will become the part of this ring system, it will then give us the product that is a highly stable system, and A at